examination of the existence of dark matter.
Okay, thanks for having me here and giving the opportunity to start off. I love that we got assigned titles. I haven't had that in a long time, and it. No, I took it as an opportunity to think about some things that I haven't for a little while. And one of the things that I've noticed is when I go to a talk by dark matter, usually about some idea about dark matter from particle physicists, it inevitably starts with a slide like this. Rotation curves are flat. And then, therefore, we need dark matter, right? The observed data is above what you expect from what you see. Then also there's clusters of galaxies and or the cosmic microwave background. Therefore, the universe is full of non-baryonic cold dark matter. And so it's kind of a broad remit to critically examine that. And so I want to try to take you on a back and forth slalom ride that goes on in my own mind, both pro and con, against this picture, which I trust we're all familiar with at this point. So the lambda CDM model of the universe in which we live in this little wedge of normal matter. All the standard model particles that we actually know about reside there. Maybe a quarter of the mass energy budget is dark matter, presumably some sort of dynamically cold thing like a Wimp. Doesn't have to be a Wimp as far as the astronomical evidence is concerned, but it does have to be pretty cold. It can't be dynamically hot like a neutrino. And the rest of it is dark energy. Now, the best evidence, not the only evidence, but the best evidence for these two add-ons is, in the case of dark matter, that the baryon density, which comes from Big Bang nucleosynthesis, which is a really well-established and one of the few over-constrained things in cosmology, does not add up to enough mass density for what we see from any gravitating measure of what's out there. So there's mass out there that gravitates that's more than the baryons. You also have to grow structure from the very smooth initial condition that we see in the cosmic microwave background to the very lumpy condition that we see today. And gravity will do that for you, but it won't do it fast enough unless you boost the process somehow by having some extra dark matter. And in the case of dark energy, I think the best evidence is the geometry is measured by the location of the first peak of the CMB, though, of course, there's a lot that built up to that. Supernova were already sort of the finishing piece of that in the 90s. Now, the attitude we bring to this problem matters a lot. So in the case of dark energy, you know, if you have the nice rational, it's like fascinating. It appears that the vacuum of space is some form of dark energy that exerts a negative pressure, causing the expansion rate of the universe to accelerate. Brilliant. Nobel Prizes all around. Or, we've discovered anti-gravity! Right? And both of those statements are correct. Right? You could take the source term of dark energy, put it on the other side, and call it a repulsive term, and have the same result, just that this sounds batshit insane.
It's not anti-gravity. It's not changing the density of it. It's the pressure. Very different.
Okay, so you're saying exerting a negative pressure is okay.
It's still the same law of gravity. It's just different matter.
So I don't think you can just. I know what you're trying to say, but that right-hand side.
Well, I wanted to get people talking. So yes, I wanted it to sound insane because it is, right? And changing the law of gravity sounds insane. I would also say it's insane to assert that there's stuff that exerts negative pressure, right? I think there's a day we would have just rejected that as unphysical. Same thing goes for dark matter, right? We have orbital motions that are too fast to explain by the visible mass. Logic dictates that space is filled with some form of dark matter, right? Well, we all have bought into that. And so it's true that space is full of invisible particles that have no place in the standard model, and we have no evidence for that in the laboratory. Right?
Just going back to the negative, because you're trying to make this argument, right? But the negative pressure business is only weird because you're thinking about it as you think in a lab. When you're doing GR and cosmology, it isn't weird. The problem is that, the density turns out to be too small, right? So you have to, if you're saying something is weird, I think you need to know what your prior is.
Yes, that's right. We really need a prior.
You
yes.
Can't say it's weird because in the context of GR, it isn't weird.
Well, I think it is weird in the context of GR because for decades we said it was Einstein's biggest mistake to have put the cosmological constant in there in the first place, and he did it for the wrong reason.
That doesn't mean it doesn't exist in the
No, I agree with that, and we can do that.
It's weird. It's almost like it's not something in your framework.
Well, it wasn't.
Parsing the word you're saying.
But no, you're right. Yeah, it's true.
No, but I know by Stacy, I mean, it's a great way to start. I'm just saying, like, he's trying to make this argument about how weird something is and what our priors are.
But it is weird.
We should be careful about what we think our priors are, that's all.
Because it's age dependent. When I was a youth, it was weird. And it was stupid if you talked about dark energy. You didn't call it that. It was cosmological constant. That was a mistake. Do not talk about that. That was the message I got as a student, right? Now it's the other way around, right? But that's my point. It depends on the attitude. And you've just proved my point for me. So two attitudes that you can take is that we have this cosmology that works so well that these dark entities must exist, right? Has to be true. You could also take a skeptical thing that this, our present understanding of cosmology is only correct if and if these dark entities exist. So we would like some laboratory evidence. So this is the dark matter tree, as I call it. This is a sketch I made over 20 years ago now. These are the roots of the problem, the empirical things that drive us to conclude that there's a problem. And up here, all the fruits of the trees, the different ideas for what the dark matter might be or the solution. And I put this on here to remind myself that I now teach an entire course on this subject. When I got to Case Western, I thought, well, we always bring dark matter in as a sort of an addendum to some other subject, cosmology or galaxy dynamics. And, at this point, it deserves to be its own subject. And then the day before class, I was like, oh my God, do I really have a semester's worth of some material here? And the answer is yes. This is all sort of more evidence that I pile on here that I do not possibly have time to discuss. But there's lots and lots of evidence for mass discrepancies. Okay. The astronomical evidence for that is overwhelming, so I'm not going to stand here and try to make the case that dark matter doesn't exist because there's no evidence. The issue, to my mind, is whether it is mass discrepancies, i.e. some form of dark matter, or if we have the dynamical equations right. That's much harder to distinguish. I'm going to argue both ways. Now, of course, the tree has grown since then. Warm dark matter, I didn't have a specific branch in here for. Before, I did already have WIMPs and axions and strange nuggets and things like that. And I always sort of thought of the observer's job as to be a gardener and sort of prune off. Okay, it's not brown dwarfs. We can trim that branch. Of course, the theorists are growing like weeds. So there are all these other ideas, and these are just the ones taken from the program. All right, so, I just cleaned this branch up. What are you doing? But for most of this time, most of us, including myself, have been convinced that the most probable answer is WIMPs. So let's bark up to the side of the tree for a bit. And, of course, this is the exclusion diagram for WIMP mass and interaction cross-section. And if those of you like me remember the Wimp miracle, this was all natural and compelling because the natural cross-section to give the right remnant density was a weak force scale of about 10 to the minus 39, which is up off the graph of this, because if you do a more careful calculation, okay, maybe it's 10 to the minus 41, 10 to the minus 42. That was fairly quickly excluded, and so did we say 10 to the minus 42? We meant 10 to the minus 44. Did we say 10 to the minus 44? We meant 10 to the minus 45. And of course, this is where we're at now. So we can keep sliding this down forever, but it sort of feels like we're in an unfortunate place that this can go on so long. So if the WIMP paradigm is correct, we ought to detect them at some point. And if we don't detect them at some point, we have to have an exit strategy. How do we decide that we've looked hard enough? All right, because in principle, we can look forever. All right, that's not really a satisfactory situation. You want to know when it's time to move on and look hard at something else. Okay, so like I say, there's lots and lots of evidence for mass discrepancies. The critical evidence I will try to get through here, probably can't, is large-scale structure growing from the microwave background, rotation curves, clusters of galaxies, and dwarf satellites. And these sort of give alternate answers in turn. So it's important to have a prior, as we've already established. In 1999, we did not yet have relevant data from the microwave background, basically only good measurements down here. But we did already have lambda CDM. We were convinced of that by the supernova data, and we were convinced that that had to be right because of a whole series of results all through the 90s that drove us in that direction. We knew what omega matter was. It wasn't 1. We knew what omega baryon was. We had a pretty good idea at that point what the Hubble constant was. And so these red lines are what we expected for lambda CDM as it was known at the time, before there were data. And as a null case, there's 0 CDM, just the known baryons. Okay.
What exactly is your no CDM model?
It's just GR without cold dark matter. It's got omega baryon as normal.
Omega baryon 0.04.
Yeah. Yep. But yeah, so the one thing I have to do to compare these straight up is the geometry, and that's why I've normalized to a flat geometry. If you're going to consider a model, right, we know this is wrong already going in, so
Why isn't the amplitude extrapolation?
I've normalized that. In fact, but this has the right normalization with if you just stick it at omega lambda.
I mean the size of the peaks.
This is a model with omega lambda as the proxy to make things flat. So it's got some ridiculous 0.96, right? If you do that, that's the amplitude you get. Oh, I see what you said. How do you grow structure? This will not give you a current structure, right? So it's normalized at the C and B time. If you grew this forward, it would not give you the current galaxy spectrum.
Normally when you make the baryon density high,
Yeah, yeah, but this is actually, yeah, so you see damping, right? That's the other thing, but there are two issues. One is that there's just damping when you have no dark matter, so there's no driving term, but you're concerned about the overall amplitude. That's what comes out of CMB fast when you do the calculation. I haven't fudged the amplitude. The problem with it for structure formation, if you just have regular gravity going forward from that initial condition without dark matters, you'll never get to today. You have to, it's true, there are many knobs, you have to watch what's going on. So what was, I had at the time posed this as a test. Do we have dark matter or not? And so until we got out past LF600, data were pretty consistent with not. But now you get out beyond that, and you certainly do, right? And so there's, I would say, lambda CDM wins ugly here. The prediction was not on. Anything within those bands would have been fine, and it misses that band. On the other hand, you cannot have a no CDM model and explain those data, and it gets worse as you go further out. Well, it continues bad as you go further out.
So what does high baryon and low baryon lambda CDM?
So, at the time, we thought we knew baryon density very well from Big Bang nucleosynthesis, and that was the number. So this is from Walker et al., Schramm's famous compilation. There's another of these things, like no lambda. It was known. Khaleesi. This is the number. This is a summation of much work. In 1991, this was a review of all the work that had come before. This was already very well established at that time.
Well,
and
in that time, people would determine the baryon symmetry or baryon content from lithium. Now it's completely discarded, right? So it's
I'll come to that. But to answer to what's high and low, right, this was what was known at the time I did the calculation. So that's high and that's low. The area of those circles is the error bar on that, right? So that was the range I considered.
Where was it on the other? One of them was on top of the first beacon.
So the low baryon, they overlap, right?
Oh, it's the two red bands.
The two red bands, right, corresponding to that range of things. There's also a range of omega matter that I considered and what mattered with the baryon fraction. But anyway, that was the range that I got for what we knew at the time. And now to fit the data now, we have to push down that second peak, and the biggest knob you have to do that is to turn up the baryon density, which increases the drag. And so that's the baryon density that you get now from a CMB fit.
Stacy, can you go back to that same question? So if you look at the 0 to 50 or 100, what happens there? Because the rise to the first peak depends very sensitively on the total matter density to the radiation density, right?
Sure.
And in your case, you don't have cold dark matter. It's just baryons. And so the matter to radiation equality is changed, and so that would change. So I'm just thinking, like, how do you even get it consistent at the lower end?
So, oops, that's a good question, which the prediction was that you would actually undershoot this, that you should undershoot this with this calculation, because this is just GR plus baryons. You still need something else funny going on, like some kind of modified gravity. And any back of the envelope thing that you do tells you you're going to get more of an ISW here, right? So the troubling thing, if you flash forward to something like Tevis, which didn't exist at the time, it's very easy to predict something up here with Tevis, right? So that happens. It's hard to get it as small as it is.
The visual impression from this is like, the first peak comes out, right? But actually,
if you do a formal fit up to L of 600, chi-square is fine. It's perfectly happy with that. Beyond that, obviously not.
Say
Even today.
Including the low L.
Including the low L. Yes, it is. Now, but the model is in the literature. I published it in, 1999, 2000, something like that. If you don't believe me, you can download the model from my website and do the calculation. Right. So this is what's changed, right? This was a big shock to me. And again, attitude matters because this was known. This was written in stone. And now we've doubled it. Okay? So, it's not so much that I would say it's a tragedy or something, but it was a bit disturbing to me. And if you look at the detail, this is where we can find baryons today, all in the stars and the cold gas, intergalactic medium, and so forth. We cannot find them all. Now, this is the baryon density published as a function of time. So this comes back to the lithium issue. The yellow stars are lithium. The red is deuterium. The blue are the CMB fits. And you'll notice that before there was CMB data, that dotted line, that mattered, there was not a single suggestion that the baryon density was above 0.02. The highest it got was 0.019 from deuterium. There was a famous debate about that. This one won out. And already at that time, that seemed a big number. You get CMB data, and all of a sudden, look what happens to the red points. Not a one of them is below that line anymore. Now, I do not know if confirmation bias is what's going on, but that's what it would look like if it were. And the people who do deuterium abundances, that's done in the line of sight to high redshift quasars. That's a community. It's very strongly coupled to cosmology. And so they're paying attention to this. Lithium, that's done by stellar people who give a flying Watchahoochy what cosmology says. And their answer is the same. So one of those things is wrong. There's a discrepancy. But it's very dangerous to say these are in great agreement, therefore we can ignore the rest.
Well, in all fairness, there is less probability that external to cosmology reasons deplete deuterium or reach deuterium in those clouds compared to the evolution of lithium and stars.
I agree with that. Astrophysically, deuterium is a better measure in that sense, so it's also easy to mess with, so you got to be sure you get a primordial sample. So, I would not make a case against lambda CDM based on this, but I do find it worrying.
But in the same time that you're not citing Walker at all, they also realized that there was an issue with the different abundances not matching up, right? It wasn't just that
people realize that, and so like I say, yeah.
So it was not a settled issue in BBN. There was this problem. So it's not as if there was a consensus. Right?
And,
it depends on how you think you're measuring.
Look, there is Yes, there was a problem then. There's still a problem. We call it the lithium problem because we've decided to believe that one.
What Maxine just said, that it's more, it's more reasonable that lithium gets destroyed in stars.
Okay, well, this is the part y'all should agree with. We haven't even got to the controversial stuff. Because, well, anyway. So look, you still need, right, there is this is what would happen. This is like a rotation curve without dark matter, right? It fails, right? You need something here. And the most obvious thing is some kind of dark matter. That gives a brilliant fit. I think we can all agree on that. Hope we can all agree with that. But we do it assuming general relativity is all we need to know. All right, spiral galaxies. Same issue. You can build a mass model. This is rotation as a function of velocity. This is what we actually see. This is the baryon density. This is a rotation curve that would be predicted by the baryons that you see, the stars and the gas. So that's what the rotation curve should be. There's no dark matter or other funny business. And again, those things disagree by a huge amount. Now, this is something I've worked on a lot lately. Galaxies over this mass range, a lot of galaxies. I don't have time to describe the sample, but there's lots of data now. And we all know this one. Rotation curves tend to become flat. That's what I hear every time I go to a dark matter talk. But there is more to the story to that and more that we need to explain. It's not just that they become flat, but they do so in a very specific way. The baryonic mass scales as a power of the flat velocity, very little scatter. And on a point-to-point basis, what you see in the baryons is predictive of the total that you get. So here are some rotation curves over a range of mass. Big galaxies rotate fast. Small galaxies rotate slow. And that's called the Tully-Fisher relation. It's fundamentally a relation between baryonic mass. So now every point is one galaxy here. Colored points are more gas. Gray points are more stars than gas. And it doesn't matter what form the mass is in. You get a nice uniform relation over this many decades of mass. And it's consistent with a single power law. Fine. I can think of ways to explain that. The thing that bugs me is that the intrinsic scatter is very small. So you see the error bars on there. You can do the error budget. You can work out what's left over. And basically, there's nothing left over. There's only an upper limit on the intrinsic scatter of this relation. It's incredibly tight.
Can you not fit that with something other than 4, like 3.7, 3.8? Close to 4, but not 4.
So now it depends on the measures you use. If you measure V flat and you measure it over this range, then it is very close to 4.
If I see a break like somewhere in the middle, like around 150. If I do something, isn't there? I'm not discussing your intrinsic scatter. It's just this form. Is it really V to the 4?
As near.
That's what you're asking, right?
Huh?
You're just asking what is the error bound.
It's plus or minus 0.1, something like that. I've done this many, many times, and it always annoyingly comes out to 4. I mean, there was a.
I've seen other people
on this data set. People use other measures for rotation blocks and stuff. This is probably one of the most.
So two things. If you look in the literature for Tully-Fisher, they are almost always restricted to this upper mass end. Then you can get lots of slopes. And if you use, as Frank says, if you use a different velocity measure, you will get a different slope.
But this is what I was sort of asking is like, isn't it, if it's possible to fit the upper end of that mass range to something like, let's say 3.6, I'm just pulling something
Yeah,
out of hat.
that works.
And it's possible it's like 3.6 and then it goes more like 4, right? Is there a strong prior that
Sure.
I think it's a power law? And the example is the 2-point correlation function in Galaxies, right? You thought it was a power law until you realized it wasn't with better data, right?
No, these are the better data. And so I have asked. I don't think that's true. I've asked this specific question because there are plenty of models that do, as you described, they bend in this line, and I'm not going to try here to test specific models. So I've asked the data. You can ask, do you want another parameter? And things like the Bayesian information criterion say, no, you do not want another parameter.
Does it also depend on the net to the light ratio?
Yes, absolutely. And so that's not an hour-long talk. That's a 10-hour-long talk. So I'm going to beg your forgiveness and move on beyond that. The thing is that for the gas-dominated things, it doesn't really matter what the mass-to-light ratio is. And anything plausible gives you something continuous here. If you choose your mass-to-light ratio really poorly, then you will absolutely see the effect that we were just talking about. Say if you make it too low, these points will come down, and then you will artificially insert a break in there. But that is something we know from stars is already disfavored.
Just to be clear, like 3.6 or 7 and 3.4, on that plot isn't going to look that different. I'm just saying.
I have a plot much later that shows you almost exactly that. But I just wanted to show the data and not throw a bunch of lines on it. Certainly 3.9 is okay. 3.7 is already rough.
Just for the non-experts, what's the selection effect that you get from the mass-to-light ratio?
So it's not a selection on mass-to-light ratio. It's just that for the galaxies that you do have in the sample, the baryonic mass depends on the luminosity times the mass-to-light ratio. So as you change that, it moves the star-dominated things up and down there. So it tweaks the slope by changing the top end more than the bottom end. These things are mostly gas, so they don't really care what M to L you adopt. Okay, so it basically, the slope pivots in that sort of sense from there.
The middle is important, right?
Sure, yeah. Yeah, it matters here. Yeah, absolutely, it matters there.
And you know, just trying to compare that. So, we're 3.7, like what would you say?
I'm just
Is it
saying
because
that.
of the modulus relation to what you get, or is it just because?
No, I mean, Stacy
His
has.
point is that it's very tight as well. Right?
No, but there's two things, right? So the tightness, is something that, I think we should all, like, this is a very important point. I'm just wondering about the B to the 4 business, right? I mean, does it really have to be 4, or could it be something different, right? Because there's a lot of models, for example, when you run, maybe Alison will talk about this, where you can get maybe 3.6, 3.7, and Stacy knows this better than anyone else, because in the literature, people find all kinds of different slopes, right? Argue what is, but 4 is just hard to get from.
So yes, from a purely empirical perspective, I've tried fitting this for 15 years. And because of the reason you've just said, I keep begging that the slope not be 4. And that's what I keep finding. To give you a specific example, Stark et al., 2009. When we first submitted that paper, we got a slope of 3.74, which I remember because I thought, thank God it's not 4. The referee came back and said, well, you need to do a reverse fit and check the slope. Dope. Well, it was 3.92. So I have tried, again, it's confirmation bias. I have a confirmation bias here. I wish I could report to you a different slope.
Did you do a goodness of fit for chi-squared versus the slope?
Yeah, sure, we've done that. And it between 3.9 and 4.04 is where it's happiest.
Delta chi-squared
I did that so long ago, I don't even remember what the number is. It's published in a 2005 paper or something. The real issue for that is a systematic, not the formal thing. It's what you adopt, what prescription you adopt for the mass-to-light ratio. Okay, so I wasn't going to make a big deal of the slope. The scatter is small. That's the thing that concerns me, because you can tune a model to get any slope that you want. It's harder to do that and keep the slider slope. So now this is the residual from that fit. Basically, for galaxies of different size at a fixed mass, you have the same velocity but different radii, and there is no variation with that. And you would naively expect that, because you're taking one component of the mass, the stars, and either stretching them out or compressing them. V squared goes as GM over R. So at least for the stellar component, that's true. And you would expect some residual that correlates like that. You don't see that, so one interpretation is that the stars have negligible mass. We can exclude that. But first, I want to point out I'm not the only one who says this. This is a model from Desmond and Weschler. Same plot, same scale, right? There's a different data set. And again, there's no obvious residual in this, but the models they discuss do predict such a residual. And it's a really fundamental point because V squared goes as GM over R. The stars are an important part of the mass budget, at least in high surface brightness galaxies, and if you start spreading them out, you would expect to see some residual in this relation, and you do not. To give a specific pair, these are two galaxies, a compact high surface brightness galaxy, a spread out low surface brightness galaxy. They're indistinguishable in the Tully-Fisher plane. Same total mass when you integrate it up, same V flat, but very different mass distribution. So here's the rotation curve of both of those things. There's the high surface brightness galaxy. There's the low surface brightness galaxies along with their baryonic mass model. So you can see the effect that I mean, just looking at the stars, you get a lower peak amplitude here. Even though the mass is the same, the radius is bigger. All right, so that goes down. But the flat part doesn't know anything about that. So from that, we might infer that the galaxies are entirely dark matter dominated. We should turn these down to 0 or something very small, have a very low mass to light ratio. But then they're living in basically the same halo, same mass galaxies living more or less the same mass halo. So within the scatter, they should have the same rotation curve, and they don't. Right? The inner part of the rotation curves knows extremely well about the mass distribution. All right, so you can't get away with that. And in fact, it knows too well about it. If you now normalize the rotation curve to the scale length, some characteristic scale of how big the disks are, they're indistinguishable. So it doesn't just know about the total mass. It knows about the distribution of luminous mass. You've got to explain all those things. This is generically true. These are rotation curves, log-log, for all the things I can put my hands on. With the color bar representing the characteristic surface brightness, ranging from low surface brightness all the way up to high surface brightness, and your eye can just see a rainbow there. It's very systematic, dependent on the surface density. Okay, so yeah, this is the part that's not so well known. So the way we found to quantify this recently is to go from the scale that turns out to matter is an acceleration scale. There's lots of things you can do that. You can take the surface photometry, so this is the surface mass density profile of this galaxy. You can turn that into the rotation curve that you would get for that mass distribution. That's that blue line. This is what's observed. And you can compare that centripetal acceleration to that, what it should be. So here's a few examples: rotation curves, baryonic mass model, observed rotation curve, observed acceleration from the rotation curve, predicted by the baryons. 1-to-1 is just Newton. If everything were on that line, we'd never have dark matter, no problem. And the point here is that these galaxies all deviate in the same way. So there's something systematic going on. And you can pile all the rotation curves for all the galaxies on top of each other, and you can't tell them apart to within the errors. So this is this radial acceleration relation. Up here, it's just Newton. The high surface brightness regions of the inner parts of bulge-dominated galaxies show no clear need for dark matter. As you move further out, you need dark matter, but you need it systematically. And for low surface brightness galaxies, they only live here. They never get up in here. And yet, even though here the discrepancy is big, you can predict what it is just by what you see.
What did you use for the mass to light ratios of the bulge and disks here?
So the particular model has a Spitzer mass to light ratio and 3.6 microns of a half solar mass to in solar units, and for bulge it's 0.7. It's fixed for everything, right? So there's no tuning or fitting or anything here. It's just saying what the data are. Now, of course, presumably there's scatter in that, right? There has to be. Exactly. And so you can do the error budget, right? So if you go through that error budget, it's incredibly tight. And about half of that error budget is just from the error bars. If you ask what's left over for stars, for the scatter in M to L, it's a little over 1/10 of a dex.
That's funny, right? Because in reality, there should be that scatter.
Yeah.
Galaxies are like that. So can I then paraphrase what you're saying as, in reality, they think to have more scatter, but somehow when you make the M over L to be one value, it seems to collapse. That seems more of a curiosity than
Well,
something.
I agree that would be a huge curiosity if it were true. Now, I did this exercise in a paper in 2004 where I only had optical data. And the scatter is much bigger there because it's harder to nail down M to L. The whole reason we've gone and done this with the Spitzer is to try to drive that down. Now, for the reason you just said, we expected this would be worse. We thought it'd be better than the optical vision, but not as good as this. This just falls out. Now, if you go and look at other people's stellar population models and ask what they think the scatter in these bands is, it's between 0.1 and 0.15 dex. We get 0.11 out of this. So it's actually not unreasonable from a stellar population point of view. It's just what you expect to happen as you go to the near infrared, which is why we did it. You can fit some arbitrary function to this. There's a scale here. And this scale is in the data. If you take nothing else away from the talk, there is a scale in the dynamics of galaxies that is an acceleration scale of order 10 to the minus 10 meters per second per second. That's where you start to break away here from the one-to-one line. Above that, you really never infer the need for dark matter. Below that, you do, and you do it in a systematic way that's predictable from what you see. And there's the scatter, right? So we can actually predict what the scatter should be, what it's observed to be, and that scatter has built into it 0.11 dex for the stellar pops. I agree, it could have been bigger. That's really weird. It's not.
I guess I was just approaching it from the stellar. I've seen other models in stellar populations, and this is where it is bigger, right?
Well,
And I wouldn't be that surprised if galaxies are not that uniform. So it just seems like, in the real world, it should be bigger.
this is the real world, Manoj.
That's from astrophysics.
No,
that's not. What that is saying is that if you put in that, M over L, then that's what you get. Right? If you put in some other value of M over L and increase the spread there would increase.
All right, well, so
Daisy's point is there should be no M over L if you make the scatter small, right? That's not how
that's correct.
But that's what I said is a curiosity, right?
And
That's a different problem to solve than saying that this is the real world.
I had a...
You're saying that if you were to put scatter in like it should be,
then this plot is going to reflect that.
scatter.
But no, we've done that. We've put in a fixed thing and asked what the scatter is, right? If you put in scatter, then you can make it worse, right? You can't magically make it better.
I completely agree that that's an interesting thing. That when you do assume this one value, why is it like the scatter goes down? But that's a different problem to solve than saying that this is what it is. That this is what it is given the MO value you've chosen.
So I thought we were talking particle physics, so I took out the slide. It has different choices of M to L. It slides things around a little bit, and if you choose it really poorly, then the scatter gets bigger.
Your Nelly paper showed that even for the Telly-Fisher, the baryonic your Telly-Fisher, if you choose a different M over L value, the slope can change pretty drastically.
If at the upper end, right? So yes, that's true.
You could have power law, it went anywhere from 3.5 to 4, depending on what the mass to light ratios were, right?
Sure, and the scatter varied with that too, and this is the one that minimizes the scatter.
I agree, but that's a different statement. I agree that it's an interesting statement. For this M over L, why is the scatter the minimum? But that's a different problem to solve.
The thing is, I thought where we are now in the discussion is that now there are series of papers like Frank and you know better that are just saying this is coming naturally from standard information process. Those were what those papers are saying. So
I
we're
don't think
not.
anyone's shown that the scatter is what Stacy's doing.
No, I mean, Carlos Frank and Navarre, they have those papers showing we all now get this tiny scatter from natural processes. That's where the discussion now.
Oh dear.
Papers, right?
Yeah, well, I think those papers are complete bunk.
Okay.
Let me be frank about that. And one signature of that is they came out instantly, right? I wrote the same paper with optical data 12, 13 years ago, specifically saying, okay, you don't want to think about MOND. I get that. Here's what you got to do with your galaxy formation models. Frank is the only person who ever attempted that.
Hey, I did it too.
You didn't show this. You showed an acceleration scale. That's not as much.
Frank had, right? I mean, and that is a lot.
But my point here is that Navarro et al. Completely willfully ignored that. And now they all of a sudden say, oh, yeah, we can do that.
Right, so I would like to know.
So
So my view of it is getting the scatter this small is not trivial at all. But that may be related to the point
Why
that Marsh is
are
pointing.
people showing now?
And I think the other point is that it's very hard to get the exact functional form correct. That you can only do if you make certain assumptions about the galaxylation process that are not entirely natural.
So all these papers, or at least two, that are coming out saying, oh, this falls out naturally from our sim, Eagle or whatever, we were not kept.
I don't like this word natural. I can believe that you can do it in simulations. In fact, I'm sure that you can if you tune things enough. That's the trick. It's the tuning. There's nothing natural about this.
The one natural aspect, I think, is that people often wonder, but why does the baryon seem to control what's going on if the dark matter dominates? And really, there is a natural explanation for that. That's called gravity. That the baryons know about the gravitational potential, they feel that, and therefore they adjust to it. And that you've often used as an argument against CDM, but I find that quite natural.
But it,
Baryons know about the
come on, Frank, that doesn't
gravity is
work.
way from unification.
No,
That's why you
it
get
doesn't.
this correlation.
If we simply took NFW halos and let exponential disks collapse into them without any feedback, that does not work. That's what gravity is doing. We need to have the feedback to change that. So, I think you're whitewashing the issue here, Frank.
I guess Frank's point is that there is a connection between baryons and dark matter.
Yes.
In the sense that larger mass halos have more baryons, lower mass halos have less baryons. There's a relation there. Right? Now, whether you get it exactly on that line or not is a different thing, right? There is some relation like this.
Sure.
Right? And so if you get the rotation curves right, you're going to get that right. You agree?
I think that's true, but of course we infer that from data, so it goes back to what your prior is. The prior we had was there was no reason to believe that low mass galaxies had a different baryon fraction than high mass galaxies. From that prior, you get it wrong. Then you say, okay, they must live in a different halo mass. And so once you start, that was what I would call tuning. Once you start tuning that, then but then it's not natural anymore. Once you start tuning, it's not natural. It doesn't satisfy my definition of natural.
Tuning to make the baryon fraction vary with galaxy.
Oh, yeah.
That's
It's observed, but the tuning is to do this. So here's the line I mentioned. Right, so that is the mass velocity relation of dark matter halos scaled down by the cosmic baryon fraction. So if you magically turned all the baryons into stars so that you could see, then they should fall on that line. Okay.
So everyone knows that galaxies.
I'm just explaining for her what it is that this line means, not that that's what happens.
I know. I was questioning his.
Yes.
We know that there's the depth of the potential well allows you to hold different.
Sure. But we infer that from these data, not the other way around. We never originally said, oh, I'm going to blow out all these baryons from these little galaxies. That was not a prediction that anybody nailed their career to. It's after we start inferring that what we observe is much smaller than that we say, oh, yeah, we can do that. So that's why I say the attitude matters, right? Once we've subsumed that into our, oh, yeah, everybody knows that, then it feels natural, but it is not. Right? And so here, this is leaping.
That we known since 1977, 1978. We've known that in order to sell the CDM paradigm, we need to have galaxy formation have a scale dependence with halo mass. So it's not something. No. It's
true we've known about it for a long time, but Momau and White model, 98, those had constant baryon fractions. Yeah, I know. And I told them that at the time because of this. But that's my point. It's not the other way around. Right? A natural presumption was that it would be constant. You can go back and find Scott Tremaine saying that in the early 80s.
Not a natural. They were doing the first semi-analytic stuff. So
okay.
That's the place to start.
So, but the point really is about the scatter. I agree. You can get any baryon fraction you want out of a model. It's getting something that does this. So this is a slope of 3, that's a slope of 4, so you can imagine, 3.5, it's not going to do it down here. Maybe 3.7 cuts it.
Or if it's too powerless, there's something different
Yeah.
on the upper end and something changing.
Or a step function, right? Look at that. Groups and clusters fall on this slope if you just give it a little nudge.
Well, no, but that's an important thing. The clusters people claim don't fall on that thing, right? There are cluster galaxies they don't look like. They don't have similar Tully-Fisher relations.
Well, this is Tully-Fisher for clusters with temperature as the velocity measure. So there's the offset, that's right. And that's why, so another way to put it is the baryon fraction is fine for rich clusters of galaxies because the green line goes right through there, right? But it's terrible elsewhere.
That's how that physically makes sense. I'm not going to argue with that
Is
anymore.
it really hard to get 4? I'm wondering why you're worrying about the 4. Can simulations do it, or are you saying that there's really needs to be some tweaking to get 4?
Well, I'm just saying that it's reflective of, basically like the question is like, what is the range here? And I think if you play with the mass light ratios, you can get different scales.
Okay,
And so,
is there
and
something-
that feeds into the scatter also. Right?
Sure, but is there something difficult about 4? You said.
Okay, yeah, in my mind, yes, because 4 is a nice number, right? It's that motivates
Yeah.
building different kinds of models if you have 4.
Sorry,
If I really knew it
3.9?
was 4.
3.9 would work for you? Or
I mean, 3.9 is just 3.9. It's a non-analytic. I mean, it's just
I agree. If the slope is 4, then this power law, the units have physical units, right? If it's just some random power law, then it's, kilometers to the 3.9 per second, right?
Massive baryon physics are required to explain it. If that gives 4, then you gotta, okay, that would be sufficient.
Well, and even that wouldn't bug me, except that's what Milgram predicted, right? What bugs me is that for galaxy dynamics, we keep having to come up with these stories that explain what he already said would happen. That's not natural.
He cannot predict 4, right?
He,
That depends on the function you use for the.
so he chose 4. So, all right, so haven't gotten around to introducing Mond, but
Yeah, there are a lot of non-experts in the room.
Yeah, yeah.
Time to go slower.
well, no, I mean, I'm basically out of time, so.
You started late.
Yes, I did. Okay. So I had a slide for this. The notion of Mond, of course, was to 13. Okay, well. Okay. So the idea in Mond, since we're already leaping to that place, which I was going to introduce more gently, try. You change the force law at an acceleration scale. So the above this critical scale, which is the 10 to the minus 10 meters per second, everything is normal. You don't infer the existence of dark matter. Below this scale, you change it in this really messed up way that seems to work. That is, basically, it's just you multiply in quadrature what you calculate from Newton times this new scale. Now, like everything, Mond was designed to give you flat rotation curves. That was the motivation. That's true for dark matter, too. The particular choice of an acceleration scale rather than a length scale is what gives you a slope of 4 in Tully-Fisher, right? At the time when Milgram did this, there were hints that the infrared Tully-Fisher relation did that, gave you a slope of 4. It did not give you a slope of 2, right? That was the only clear statement. So he went with 4.
Just to be clear, the constant acceleration doesn't give you a 4. It's the functional form, right? You could have chosen it to be like gn squared a naught to the 1/3, right?
Yeah, you have to have this asymptotic form, though, to give you flat rotation curves, right? This asymptotic form is what makes the rotation curve flat.
The potential, right? You need to feed it to some transition. That's how you get well, that's how you get artificial.
Well, you could. Yes, that's right. You could get other Tully-Fishers. You could make other transitions that gave you a slope of 2, a slope of 3, whatever, right? But once you do it, you're stuck with that. It could come out to 3.9, and then this is wrong, right? But the other thing that really got me interested in with this is that the dependence on R drops out of this. You can do that math in your head if you don't believe me, right? And so the lack of residuals with size is the natural prediction. That's what gets me, right? And that was a true a priori prediction, as was the form for radial acceleration relation. That could have come out to be something different. And then I wouldn't have to be defending this other guy's theory. It's not my goddamn theory, okay? But it does predict things that I see, and it would be dishonest for me to say otherwise, right? These things just come right out of it. Now, going back to what simulations do, it would take, again, several hours to review everything that's been said so far. This is, I think, one of the more credible attempts to do this, very recently using the massive black 2 simulations. And it sort of generically illustrates what happens. The scatter they get is impressively low. I didn't expect that. So they've done better than I expected there. But this is what their simulations show. This is what the data show. That's a clean miss. Well, I can only tell you what they're doing. Okay, one thing at a time.
Is there an understanding of where the scale, acceleration scale comes from in the simulation?
Yes. So could you explain? Maybe I'll talk about it in my talk. So that is the thing I did back in 2001, is to show that there is that scale, and it just comes from the growth of structure. So if you do like V max square over R max square, you get like 0.3 times C times H. That's just a function of the power spectrum and how long you've had structure to grow.
But that has nothing to do with the baryons. This is all about the baryons.
We'll talk about it when we do the SIDM. I mean, I'll show you the same plot. No, but not
well,
they're living in the halo.
Sure.
Let me separate out two questions. One is about like the shape and the what is the scatter. Right? The other thing is about what is the value of A naught, which is what you're asking. Why is it that value and not like 20 times larger? And that I'm claiming that's just simple structure formation. If our power spectrum was very different, it was tilted differently, we have more time to grow, it would be different. That's the stuff I showed back in time.
All right.
You can take this idea of a halo using computer externalization, or like Luminosity and Galaxies.
Well, look, I don't doubt that we can get the simulations to give the right answer. The question to me is whether that's satisfactory, right? Because my experience playing with this is like it's squeezing a tube of toothpaste. You got no scatter here, so you smooth the toothpaste out tube, and it looks great. But all you've done is pushed a problem somewhere else. So, right, if we're going to invoke feedback, say, to do this, then we've created a new observational problem, which is to go and check that feedback actually works in the way that we need it to as we've programmed it into the simulation. Okay, so very quickly, dwarf satellites. There's the missing satellite problem everybody's heard of. I'm not going to talk about that other than to say that this is a pretty widespread problem because it's true in the field. For those who are non-experts, these are the tiny puffballs that are in orbit around the Milky Way and Andromeda, tiny by astronomical masses, stellar masses of 100,000, give or take a bit. Now, in lambda CDM, we know that the relation between the halo mass and the luminosity has to be nonlinear in order to get that function there. So this is what's predicted, some range here. This is from Tolru et al. So for a 10 to the 10 solar mass halo, you get galaxies living, well, you get 1,000 solar luminosities, you get 100 million. There's a huge range there in the scatter, right? So tracers of the mass should not correlate well with the luminosity, right? It should just be scattered down there with a very small hint of a slope. In MOND, it's the other way around. All you got to work with is what you see, and so what you get for a velocity dispersion is predictable from that. So, does this work? It shouldn't. In recent years, people have surveyed the region around Andromeda. This is a PANDA survey. And they started discovering a bunch of these satellites, brand new. And I realized there was a period when they were discovering things that I could make an a priori prediction. They tell me the luminosity, I can use MOND to predict the velocity dispersion. I tried to do that for lambda CDM2, and I couldn't for the reason I just gave. You could say, it's 10 kilometers a second plus or minus 10. Okay, so this is the measured velocity dispersion for Andromeda 1, 2, 3, 4. There are multiple measurements, plus the prediction. That's how it came out. So green is good, red is bad, yellow is not enough data to really tell yet. Everything after about 19 here is a priori, right? I said that is what the velocity dispersion would be in print before it was measured. And in all those cases, it comes out fine. The only case, well, there are two cases where there's red. In this case, the data disagree. In this case, this is the one that just, there's a prediction. I can't change the prediction enough to get it to agree with that. So if you hate MOND, you'd say, okay, that one case falsifies it. But why did it get these right? These are predictions that you can make with MOND that you cannot make with lambda CDM. You cannot look at a specific dwarf and say it'll have this velocity dispersion. All you can say it'll be around 10 plus or minus a lot. Okay, so this is really my problem. I would love to believe in dark matter again. My life would be so much easier. Why does this happen? It should not. No, that's just the color is if they're in 1 sigma or not. The size is just a highlight.
I missed something. Where is the prediction? Green circle.
The predictions are either green or open circles, depending on whether you're in the external field effect of MOND or not, which is an additional test. Didn't want to go into. So there's the prediction. But the data have a little number next to them for the number of stars that went into that measurement, right? So some of these things are really well measured, 212 stars there, 8 stars there. Right?
For example, why is that 24 a good?
Because it's within 1 sigma. It's 42 stars. They overlap at 1 sigma.
That's an upper limit that's 24, right?
Which one? This one? Yeah, this is an upper limit. Yeah, that's an upper limit. Okay, I will try to finish up. So, in fact, that was where I was going to end anyway, so let's just call it that. And this is, I didn't even really get to talk about the clusters, but if I put on my cosmology hat and I look at all the usual things, then I say it's got to be lambda CDM. If I put on my galaxy dynamics hat and I see all these kind of predictions actually come true, that's usually how we keep ourselves objective in science, right? Is to make a prediction ahead of time. And there's clear evidence in both ways. I don't see how you do the CMB without some form of dark matter. But I don't see how we explain the predictive power in MOND with something that's not MOND. Maybe we can do it. But it's not just that, it boils out of that. You can do this on a case-by-case basis. So this is probably a good place to end. Any of y'all know Tom Shutt? Tom Shutt's a dark matter detection experimentalist who was a colleague at Case for a while. But we met because his daughter and mine were best buds in school. We would say that we don't bring our work home with us.
Dark matter does too exist. Dark matter didn't exist. And it existed, but not present in all the
Okay, so we can continue that discussion now in the same tone. So thank you for your attention. Yes, there have been plenty of questions, so I'm